Hello, welcome to Inside Java. My name is Delabassee and I'm your host for this fifth episode. An important change in JDK 15 is the Z garbage collector, which is not experimental anymore and is now ready for use in production. To discuss ZGC, I have with me the project lead, Per Liden. Per, welcome to the show. Can you please introduce yourself?
Sure. First, thanks for having me. So I'm Per Liden. I'm part of the Java platform group at Oracle, and I'm part of the team developing the Hotspot JVM with focus on garbage collection. And I'm lead for the ZGC project. And I'm based in Stockholm, Sweden.
Now, garbage collector is to me a pretty complex space, so I'm curious, how did you end up working on GCs?
Well, so I joined Oracle more than 10 years ago by now, and I joined the JRocket team. So that's the team that was developing the JRocket JVM. And I started actually working on something called JRocket Virtual Edition, which was a version of JRocket that ran without an operating system. So you could run it right on bare metal on our hypervisor. And then when Oracle acquired Sun, the JRocket team and the Hotspot teams merged, and I eventually ended up working on garbage collection.
Okay. So you're the ZGC lead, and before we dive into the details, I would like to start with a critical question. ZGC or ZGC?
Yeah, this has come up a few times, actually. Well, so there's no preferred pronunciation. Both are fine. Personally, I usually say ZGC, but a lot of people say CGC, and I guess it depends on which side of the pond you're on.
Well, you know what? I'm also from the ZGC team, so let's settle on ZGC. Okay?
Sounds good.
Okay, so ZGC is per se not new. What I mean by that is that it has been introduced in JDK 11. Back then it was on Linux only, and since then it has evolved. And the big news today is that ZGC is now production ready in JDK 15. So maybe it's good to do a recap over the history of ZGC.
Right, so a little bit of history here. So as you said, it was initially introduced as an experimental feature in JDK 11. But of course, many years before that, we had worked on ZGC for a number of years. I think I actually started prototyping ideas for how to make a low latency GC and prototyping various types of load barriers. That was in late 2013. So, then this work, of course, grew from there, and it eventually became an OpenJDK project, and we sort of published all our code. And then sometime after that, it was actually integrated into JDK 11. And after 11, a lot of things have happened. So a bunch of new features, enhancements, support for all the other platforms, Windows, Mac OS. The ARM 64-bit CPUs were also supported. Things like supporting uncommit of unused memory wasn't part of the initial release in 11. That came into 13. Concurrent class unloading was also a feature that was added in, I believe, 12. So anyone who tried out 11 and thought that was good should probably try out 15, and it will be even better. And, in 15, this is a sort of a big step for the project. We've been working many years on this, and it's now finally a production-ready feature in JDK 15.
Mm-hmm. Okay. So before we go into some details of ZGC, maybe it's a good idea to explain in a nutshell what ZGC is. What are the goals of ZGC?
Right. So ZGC is a low latency garbage collector, and the phrase low latency, of course, here means that it has very low GC post times, so it will not be stopping your application for very long times. And the initial goals we set up when this project first started here way back was that a post should never be longer than 10 milliseconds. The other side, or another goal of ZGC, is that it should be able to handle very large heaps. Not just very large heaps, but small heaps too, and sort of basically any size of the heap. But the collectors back then were typically very bad at handling very large heaps, and that's something we wanted to address. Finally, the current GCs or have so far been kind of tricky to tune sometimes. They expose a lot of GC tuning options. Not that many people know exactly what all of those do, and we see them being misused sometimes, and people thinking they have figured out the correct configuration or an optimal configuration when in fact that's not the case. So we wanted to make ZGC very easy to tune. Preferably, it should just work out of the box, and you shouldn't have to care about specifying a lot of tuning options. So that's something we've worked on quite hard for ZGC, and we do expose a few configuration options, but it's very few compared to the other GCs.
Okay. So if I recap, low post time, being able to handle a small to very large heap, and the ability to easily tune the GC. But I guess that nothing is free. So what is the price to pay to achieve such benefits?
Right. That's sort of designing a GC and sort of optimizing, in this case, for low latency and the scalability. That comes with a price, and it's all about it, making trade-offs here. So we are sacrificing a bit in terms of throughput. So compared to the other GCs that are more focused on that. So if you have a pure, throughput-oriented workload, then, parallel GC or G1 is probably going to do a better job than ZGC. But on the other hand, if you're sort of interested in having low post times, because you have, response time requirements on your application, then ZGC is probably the one you want to look at.
Mm-hmm. Makes sense. Well, I know it's very complex, but can we somehow peek a little bit under the hood of ZGC?
Sure. So sort of from a high level point of view, the ZGC algorithm is, the most important part of it is that it's concurrent. So it's a concurrent GC, meaning that it will not stop application threads while it's collecting garbage. And that's not 100% true. We still have pauses, but those pauses are so small that they're basically noise in the background, and other things you do will basically be much worse than the GC pause times. So this is a tracing collector. Basically, it means that it will walk the entire object graph on the heap to figure out what's live and what's garbage. It's compacting, so it will be moving objects around on the heap to fight fragmentation and to free up or sort of make large contiguous chunks of memory available for reclamation. Today, it's single generation, so it does not divide the heap into a logical young and old generation. It's just one big space. And that's perhaps something we can get back to. That's something we're working on changing. It's also a region-based collector, just like G1, but it's the concept of regions here is slightly different. ZGC doesn't have a fixed region size. Instead, it can have a number of different region sizes on the heap at the same time. And that's one part of the reason why ZGC is pretty good at handling very large objects of different sizes. And this region scheme we have in ZGC is slightly more flexible. ZGC also has NUMA awareness, which is good on big systems where you have the cost of accessing memory depends on which core you're on. That basically means that whenever a Java thread is allocated in an object, that object will end up in memory that is local to the CPU that this thread is executing on, and that, of course, will lower the memory latencies when the application then accesses this object and does things with it. This NUMA awareness can, in the future, also be extended to other things like, when ZGC is doing marking, we can make sure that marking threads that are accessing the heap accesses part of the heap that belongs to the NUMA node that thread is executing on. The same is true for the relocation phase, where it's moving objects around. And finally, ZGC is using colored pointers and load barriers as the two sort of main techniques to achieve concurrency. And so load barriers or GC barriers in general, that's basically a small piece of code that the JIT will inject into the code stream to communicate or handshake or have some kind of coordination done with the GC. And in ZGC's case, the type of GC barrier we have is a load barrier. And that means that whenever the application is loading an object reference from the heap, the JIT will insert today 2 instructions to coordinate that activity with the GC. And the reason we need to do that is that we need to detect, since all of this is happening concurrently, it could be that the object reference you just loaded, you can't just dereference that because that object might have moved, or it's about to be moved, or it needs to be marked, or things like that. So there needs to be a quick check to see if it's okay to access this object. And if not, the application thread will actually step in and say, okay, this looks like an object I can't dereference just like that. I need to communicate with the GC to make sure I know where the object now lives, if it has moved, for example. Or if it's about to be moved, the application thread can actually step in and do sort of work on behalf of the GC by moving the object and then proceeding. So it never has to sort of wait for the GC to do anything. It just needs to make sure either I can access this now, or I'll step in and help the GC along to do some work here. And of course, colored pointers sort of goes hand in hand with this. That's the colored pointers basically mean we're using some of the otherwise unused bits in 64-bit pointers, and we store metadata there. And these metadata bits basically tells us something about the object this reference is pointing to. And in ZGC's case, we're encoding a small state machine there, basically describing which state the reference is and how that compares to which state or which phase the GC is in. And by using that, we can determine if it's okay or not to dereference an object reference once we have loaded it.
Okay. So can we talk a little bit about post time? So you said that the post time were not exceeding 10 milliseconds. That was the original goal, right?
Yeah, so that was the original goal. And that goal was, set up quite a few years ago by now, and things have progressed. We've made pretty good progress on reaching that goal. In fact, most of the workloads we run on never even comes close to having 10 milliseconds as the max pause time. It's usually, in the low single-digit milliseconds, and average pause times are typically, 1 or 2 milliseconds.
What is happening exactly during those pause time?
So today in JDK 15, the only thing we do there is basically scanning thread stacks. So whenever the GC starts, for example, the marking phase, it needs to understand, I need to find routes to the object graph so that I can then walk the object graph on the heap. And those routes are typically, local variables and registers that belongs to each thread. And those in turn live on the thread stacks. So we need to pause all threads to scan their thread stacks because, at least in 15, we can't have threads running or having them actively using their thread stacks while we're scanning them. That's what we do during pauses, find routes in thread stacks so that we can start marking. And the other time we do scan thread stacks is in the relocation start phase. Basically, when we want to move objects around on the heap, we again need to find the routes on the thread stacks because those need some special treatment.
Okay. You said today. So does that mean that is going to change?
Yes. Scanning of thread stacks is basically the only thing we had left in the pauses. That's potentially expensive work. That work scales or increases with the number of threads you have. And especially if you have, thousands of threads and the thread stacks are very deep, then, that can take some time. And we've seen when running on very large machines which have, thousands of threads running, we can see that we're very close to going over the 10 millisecond max pause time. And so we've sort of invested quite a bit in addressing this. And starting with JDK 16, our goal is no longer to have max pause times of 10 milliseconds. Instead, it's having max pause times of 1 millisecond. And of course, to reach that goal, we can't be doing thread stack scanning in pauses anymore. So there's been a JEP in the works for some time called JEP 376, concurrent thread stack processing. That JEP is addressing exactly this. So it's moving out the thread stack scanning into a concurrent phase. So The GC pause after that will basically more or less execute in constant time. And all the cost of working or walking the thread stacks will be done in a concurrent phase. In other words, while Java threads continue to execute. And of course, there's the appropriate handshaking and communication between the thread and the GC while we are walking these thread stacks. Because of course, you can't just poke around in a live thread stack just like that. But all of that has already been integrated into the JDK mainline repository, which is eventually going to become JDK 16. So we're really excited about that. And or when we reach that point, it means that regardless of what you do in your application, it doesn't matter for the GC. The GC pause times will be completely unaffected by that. And that's the first time in Hotspot's history. And once we reach this point, we can basically say that GC pause times will be a thing of the past.
And that's something that has been integrated in OpenJDK in the mainline. So that means that in next early access JDK 16 build, we can already start to use it, right?
Yes, that's true.
Cool. Now, you say that Posttime do not include with the heap or live set size, but as I understand, today they do include with the root set size. Is that correct?
That's correct. And that's what I was alluding to earlier. So the root set size is roughly equivalent to the number of threads the Java application is running, or the Java application has started right now. Today, we do scan those thread stacks in a pause, but sort of in the next JDK release, we won't be doing that anymore. That does mean that in JDK 15, we are still sensitive to the root set size. But with JDK 16, regardless of heap size, live set size, root set size, or anything like that, it will have zero impact on the GC pause times.
Okay. Now something else. Can you contrast and compare the GC concurrent phases with other garbage collectors that Oracle supports in OpenJDK?
Sure. So the two other Oracle-supported GCs in OpenJDK that does anything concurrently is basically G1 and CMS. And CMS is, that was actually removed in JDK 15. Removed in JDK 14. But let's mention CMS in this context anyway, because it might be interesting. So G1 and CMS also has concurrent phases, but they only do concurrent marking. And they only do that when they're marking their old generation. By the way, CMS also had concurrent sweeping, but it doesn't do compaction. But so whenever G1, for example, wants to move objects around, compact the heap, that is all done in a pause. Then there are other things like reference processing, and that's when the GC takes care of the soft, weak, phantom, and finalization. That's also in ZGC a concurrent thing, but all other GCs do that during a stop the world pause. And, you can say that, is that too bad? Or, well, yes, it can be very bad. So the processing of finalization, that actually has a worst case of scaling with the live set size. So if you have a lot of finalizers on the heap, you can spend a lot of time doing reference processing, basically. But with ZGC, that is never a problem because it's all done concurrently.
Mm-hmm. Okay. So you mentioned G1 and also CMS. So maybe it's a good occasion to recap which GC should be used for which type of workload.
So the 4 GCs that Oracle supports is Parallel, Serial, G1, and ZGC. So if we start with Serial, that's a GC that is optimized for low memory footprint and low resource usage in overall. It uses a single thread to collect the heap. That's typically a collector you would be interested in looking at when you're in a very constrained environment, like an embedded system and something like that. Then we have Parallel. That's, as the name suggests, that uses multiple threads to collect the heap, but it's all done stop the world. So it's a collector optimized for raw throughput and not for latency. Then we have G1, and that tries to strike a good balance between throughput and latency. It does some of the work, like I mentioned here before. The marking phase for old generation is concurrent, but it still stops the world to collect the young generation and collect the old generation. But that's the default collector, and that typically offers a good balance between throughput and latency. And then, of course, we have ZGC, which is addressing the low latency part of the spectrum.
Okay. So if I want to use ZGC, what should I do? Which hotspot flag should I use?
Yes. So there's a flag called use ZGC. So -XX : plus use ZGC, like you enable other features or collectors. That's the main flag to enable. And then, of course, as I alluded to earlier, we've tried to make this as easy to tune as possible. So in the best of cases, you don't have to do anything more than enabling it. But there are two other options that you might want to look at with the emphasis on setting the max heap size. So -XMX. And setting the right heap size is important because you want to have, of course, enough memory, enough heap to cover your live set size. Otherwise, you'll just run out of memory immediately. But the other side of it is that you need to have enough headroom in the heap to be able to keep up with the current allocation rate. Because unlike Stop the World GCs, allocations will continue to happen, and the GC needs to be able to service these allocations while it's collecting garbage. So it needs basically enough headroom to service those allocations. And exactly how much headroom that is, it's impossible to say because it all depends on the allocation rate of your workload and how big the heap you have or how large the live set is, basically. So it's all about finding a good balance between not wasting too much memory and at the same time keeping up with the current allocation rate and not having to collect too often. The other GC option you might want to look at, but this is sort of second to setting the correct max heap size, is setting number of concurrent GC threads. And this option basically tells the GC how much CPU time you're willing to use for collecting garbage. And if you set this number too low, then there's a risk that the GC won't be able to, again, keep up with the allocation rate. It's not collecting garbage as fast as it is created. But on the other hand, if you set this number too high, there is a risk that you will basically steal too much CPU time from the application. So those are the two main options you want to look at. There are a few other ones, but these are the ones that matter by far the most. And again, with emphasis on the setting the max heap size is by far the most important one. Next, you want to look at concurrent GC threads. And if you get those two right, then you're basically done.
Okay, so about getting those right, maybe we should discuss a little bit about observability.
Right. So, of course, ZGC offers GC logging like the other GCs do. And I usually recommend one or two modes. If you just want to have very basic information, one line of output per GC that is happening to sort of keep an eye on it, you can use -xlog GC. And if you want more information, more details on what's going on, and to understand better, how, if you want to increase the heap size or how the GC is doing overall, then you can enable the -xlog GC star option, because that will enable a lot more logging. And you'll see, for example, the current allocation rate of the application. You'll see how long each of the GC phases took. You'll see how the heap has evolved throughout the GC cycle, how much was live, how much was garbage, and so on. So that can give you a pretty good insight into how the GC is doing. And of course, there are also a number of JFR, so flight recorder events that is emitted by ZGC each cycle. And you can, of course, enable those and observe those in tools like Mission Control to get a better understanding of what's going on.
Okay. So I think we have a good overview of ZGC, where it stands today. So it started as an experimental hotspot feature in JDK 11. Back then it was on Linux only. Today it's a production feature supported on all the platform that Oracle supports. So that is Windows, Linux on ARM, and Mac OS. We already discussed a little bit about some of the upcoming features, but maybe it's good to discuss a little bit about the roadmap.
Right. So the two main things we have on the roadmap right now are sort of two big projects. That's, as I mentioned before, concurrent thread stack scanning. That we have, as I also mentioned, integrated into the upstream JDK already and is targeted to be part of JDK 16. And that will make a big difference for post times. And by the way, I can expand that a bit. So once we have concurrent thread stack scanning in place, I said that we occasionally observe max GC pause times close to 10 milliseconds or so. Our testing with concurrent thread stack scanning on very big machines with terabytes of heap suggests that we're after this going to have max pause times below 1 millisecond. So we see max pause times of about half a millisecond, so 500 microseconds, and we see average pause times around 100 microseconds, so 0.1 millisecond. So that's a pretty nice improvement. And as I mentioned, if you have a workload where response times is a critical thing for you, then ZGC can be a game changer here. And as I mentioned, problematic GC pause times will be a thing of the past. The other big thing we have on the roadmap is generation of ZGC. And this is still under development in sort of a research phase. And we're looking at adding generations to ZGC. So logically dividing the heap into two regions, a young generation and an old generation. And by doing that, we can basically collect young generation where this whole thing with generations builds on the assumption that most objects die young. So most objects are short-lived and can be handled in a young generation so that we only collect the young generation most of the part, which is a lot less or less expensive because the live graph we need to walk there is smaller. And then occasionally we'll be collecting the old generation. And by doing this, we'll basically be able to handle higher allocation rates for the same headroom, or flip it on the other side, you can use less headroom for the same allocation rate you have today. So we'll be using less memory, basically. The other thing is that we'll be using less CPU because the number of CPU cycles spent per collected byte will be less because most of the objects in the young generation will have died, so there's fewer objects to mark through, and hence we'll be saving CPU cycle compared to walking the entire object graph, including the old generation where we would be walking a much larger life set. So those two are the most important features we're working on. And of course, we have a bunch of other things on the roadmap, but those are sort of small optimizations and improvements here and there.
Okay. Well, guess what? Time flies. It's already time to wrap up. This show is called Inside Java, so I'd like you to give our listener a peek inside the day of Per.
All right. So, these days, most of us are working at home. And so that's a bit different from what it used to look like. But most of my days I spend, writing code, reviewing code, doing the occasional presentation. And of course, I have a bunch of talented colleagues. And even though we don't meet face-to-face these days, we do a lot of emails, Slack, and Zoom meetings to discuss code and to discuss solutions. And sort of outside of work, I spend a lot of time with my daughter and my girlfriend. And I guess my main hobby, you could say, is playing with radio-controlled cars. So whenever time permits, I try to play with that, and occasionally I'll compete too.
Compete, really?
Yeah, there are actually radio control car competitions going on. So, and here in Sweden, you actually need to have a license to compete. So I'm actually a licensed RC car driver.
Okay, so you have a RC driving license.
Yes.
Per, thanks for your time. I really enjoyed this conversation.
All right, thanks for having me.
You're welcome. Thanks again, Per. Bye.
Bye.